Alright, so today we're going to continue statistics. So what I want to go over today is called the probability density function. So for a discrete variable, sometimes it's called the probability mass function. But basically, I want to give you some terminology about probabilities, right? So if you assume that the notation is that if event A occurs, then the probability of A is equal to, whatever. So so let me write this differently. The probability of A is probability that A occurs. Okay? So that's the probability that A occurs. If you do PA bar, that's the probability that A does not occur. Okay? If A and A bar are mutually exclusive, and what I mean by that is, like, let's say A is is rolling a 5, right? Then you have a finite probability that you're going to roll a 5, and then A bar would be rolling anything else. Okay? Now, because this is exhaustive, right? You can either roll a 5 or something else. There's nothing else you can do with a 6-sided die. Those two events are mutually exclusive. So you can roll a 5 or you can roll something else. You can't roll both. There's no overlap. And so basically what it means is that if mutually exclusive event, then it means that the probability of A is equal to 1 minus the probability of A bar. And so you think about this, what's the probability of A? Well, the probability of rolling a 5 is obviously 1/6, and the probability of rolling everything else is 5/6, and the reason why it's 5/6 is because there's 5 other numbers that you can roll. Now, if you use this equation, you would get 1 minus 5/6 is equal to the probability of A, and it's easy to see if you just do some common denominator fractions that that's 1/6, right? So that equation shakes out, okay? Now, there's a couple other things that you can do with this notation if you'd like. I don't really think it's important. What I really want to get to is probability density functions, which basically says what is the probability of any event? What is that equal to? And there's a couple things that you can do with this. I do know that if I take, because this is a discrete variable, if I sum all of the possible events and I sum all of the probabilities, I'm going to get 1. And the reason why I'm going to get 1 is because I know if I have a variable that's discrete, then I know that the probability that x will attain any of those values, if I add them all together, one of those values is going to come out, or it's going to occur. One of those events is going to occur, which means that they all have to add up to 1. So it's basically saying, like, what's the probability of rolling a 1 on a die, plus the probability of rolling a 2, plus the probability of rolling a 3, so on and so forth, all the way to a 6, that's equal to 1. I'm going to roll a 1, some number between 1 and 6. And if I add them all together, I'm going to get 1. Okay? So that's one little notation there. The neat thing about this then is that the mean, right? And remember, the mean we did in the last video was the average of all the summation of all the values divided by n. It turns out you can also do the summation I equals 1 to n of the value itself times its probability. So if you know what the probability is, you can actually compute what the mean is. So I remember in the last video I was saying that if you roll a dice over and over and over again, I feel like the mean will be like 3.5. You could actually do this out and compute this analytically. You could compute what the ideal mean is rather than doing it numerically or something like that, or just rolling a dice 1,000 times. You could just compute it this way. You could add up all the different probabilities. And it'd be pretty simple because the probability of an event occurring is just 1/6. So it's just, you would actually just factor out the 1/6. And then the xi would be a triangle number, 1 plus 6 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6, and then all of that divided by 6, so whatever that number is. You can do that at your leisure. And that would give you the mean of the, again, this is for a discrete random variable, okay? The variance, sigma squared, right? So sometimes people call sigma the standard deviation and sigma squared the variance. So the variance, or some people also call it the expected value, is going to be the summation I equals 1 to n of xi minus mu squared p of xi, okay? And again, that's very similar to what we had before, except now we've got the probability function in there, okay? So now what happens if you, so these are for discrete, right? You have a discrete number of n's. Well, if you don't have a discrete number of different values that the number can obtain, then you have basically an infinite number of different values that xi could take. And just like in calculus when you learned that if you take a Riemann sum and as the dx goes to infinitesimal values, the Riemann sum turns into an integral. And so this is kind of called, for discrete variables, is called a probability mass distribution. When you go to continuous random variables, you end up going to a probability density function. And so that's what I'm going to show you here. I'm going to take a picture of this real quick, erase, and then keep going. Let's see, so boop. Rocket the beacons for the win. Okay, hit next. 316. Transcribing. Ooh, it's transcribing. Come on, internet. There we go. And it's in the cloud, which is just somebody else's computer. Alright, let's change colors here just because I can. Alright, so the idea is, if I want to know, if I have a discrete variable, I'm going to have like a histogram, right? I'm going to have a variable that has a discrete number of chances to get there, right? So rolling a dice, the probability is 1/6. So I'm just going to get, you know, if I roll the dice 6 times, ideally I would get each number once, which is obviously impossible, but well, not impossible. I guess you could compute it. It'd be like 1/6 times 1/6 times 1/6, 1/6 to the 6th power. Anyway, if I have xi here and it's continuous, I'm not going to get histograms. I'm going to get some sort of function here, okay? And I'm going to call this f of x. Okay, so that function as a function of x is f of x. Okay, so this is x on the real axis here. So then if I want the probability, let's say I take a and b here, I want the probability that my variable xi is going to be between a and b. Because remember, a continuous random variable cannot be, right? The probability that xi equals a is 0, right? If I look at, yes, there is a, like the, so this is what might be kind of confusing. F of xi is definitely not 0. Okay, sorry about that. My SD card ran out of memory. It looks like I've only got 7 minutes to get through this lecture, so I guess I'm going to try to get, I'm actually almost done, which is fine. Anyway, I don't remember where the video cut off, so I'm just going to repeat and I'll stitch it later. So the idea is that the function of this is a PDF, probability density function. The function evaluated at a specific number is non-zero, the function there. But the probability that my continuous random variable will land on that is 0. And so instead, I need a range. I need to say, what's the probability that I'm going to fall within 2 things? And you can kind of see where this is going, right? I want the area under this curve. So I just integrate from a to b, f of x dx, okay? And that gives me the probability that I fall within there. So then just like the other equations, I can get the mean. Instead of using summation, I just integrate from minus infinity to infinity. Right now I want the entire spread, and I do x, f of x dx, okay? And that gives me the mean. The variance, same thing, is going to be minus infinity, infinity, x minus mu squared, f of x dx. And so if you remember, I wish I still had this written down, but if you remember from the discrete random variable, instead of integrals here, we had summations, and we were just summating over discrete numbers here. But now that since we have this continuous random variable here, we have to do an integral, okay? The cumulative distribution function, the CDF says things like, what is the probability, right, that x is greater than a? That's what I want. So instead of between a and b, I want what's the probability that I'm going to be, and actually let me do less than a. Just the book doesn't write this, but I want to do less than a. So basically it's saying draw a, give me the cumulative distribution all the way from minus infinity up to that point a. And that is called f of a, which is the CDF function. Okay, and it's equal to, and I have to be careful here with my notation, it's equal to minus infinity to a of f of x dx. Okay? And that makes sense. Here, you're going from a range, and here you're going from a to b. Here, you're going everything off to minus infinity up to a, and so you're going from minus infinity to a. And so this kind of gives you a cumulative distribution function. And these are kind of neat to plot things like this. Okay? I'm going to stop here. There's a couple example problems that would be interesting to work out, but I'm just going to skip over those for now, and my plan for these lectures is kind of just go over the theory, and then and then just assign homework, and then if you have questions on the homework, then you can ask me to work out a problem. And if the homework problem ends up being very, very similar to the example problem, I might just work out the example problem and to say like, hey, this is very similar to the homework problem. Cool. So that's the statistics lecture for today. And after this, I'm going to start talking about different kinds of distributions like binomial, Poisson, and finally the Gaussian distribution. And that will be it for distributions for this week. Okay? Have a good one.